Welcome back. So in this lecture, as part of our module on the special topics, we're going to talk about min-max optimization and their connection to the training of generative adversarial networks. So what's the motivation? The motivation is that we want to kind of go from supervised learning to generative modeling. So what do I mean by that? So far, in at least implicitly, in many of the scenarios we talked about, many of the training and optimization scenarios we talked about, we assume that we are training tasks of this form. Okay, so we had basically a minimization problem where we want to figure out the best set of parameters such that we are fitting the data coming from a certain distribution, a certain data set, well on average. Okay, so this was basically our empirical risk minimization problem, if you will. Okay. And basically, as we said early on in the course, in the context of supervised learning, the implication is that we are kind of learning parameters of a parametric model, so let's call that A with parameter W, that aims to learn the unknown rule between the features and labels. Okay, so something like that. So as part of solving this training task in equation 1, then our hope is to minimize the distance between our parametric model and the true yet unknown feature label rule. Okay, so essentially this is the quantity that we are minimizing, a distance between an unknown and a parametric quantity. Okay. Now in generative modeling, the goal is kind of similar, if you will, except that instead of basically learning the rule between features and labels, we want to, let's say, learn the underlying data distribution itself. Okay, so let's call that PC. Okay, or and this is more practical, we want to learn the ability to sample from it. Okay, so we don't necessarily need like an analytic form for a distribution, because in practice it is difficult to do that, and analytic forms don't even exist. And it only suffices to, let's say, learn the ability to sample from the underlying distribution. Okay. So in some sense, then, if you want to basically understand what kind of a methodology we need, or what kind of an optimization problem we need to think about in order to model this task, it is useful to think of, let's say, our underlying data distribution Q as a true rule. Okay, and then a natural question, again, given an analogy with supervised learning, is to use a parametric distribution. Let's call it PW, that approximates Q well. So this should have been Q. Okay, so Q is the underlying data distribution that we want to learn, so the unknown rule, if you will, and PW is our parametric distribution that we are using to approximate the underlying data distribution. Okay, so in particular, let's say we can come up with a training problem that finds W, the set of parameters that minimizes the distance between our parametric distribution P and the underlying unknown distribution Q. Okay, so this is almost very similar to what we were doing in supervised learning. And this is precisely what we do in the field of variational inference. Okay, so in variational inference, you pick your favorite parametric distribution. Could be, for instance, Gaussian distributions, where the parameters are the mean and the covariance metrics. And your goal is to fit that to the data that comes from some unknown distribution. What do we mean more precisely by saying that we want to fit? Basically, you want to minimize the distance between these two distributions, and you're going to perform this. So you're going to basically minimize this objective function, where D here is some notion of distance or divergence between distributions. Okay? So it's not necessarily the Euclidean distance that we would use in, let's say, in regression problem or cross entropy loss. It is some general notion of distance or divergence between distributions, for instance, the KL divergence that we have seen in numerous contexts so far in the course. Okay. All right, so let's talk about some notable examples of these distances between distributions. Broadly, you can think of them as being as belonging to two different categories. Okay. So first of all, we have F divergences, which basically says that the distance between Q and P can be written in this particular form: the expectation with respect to P of some function of the ratio of Q and P. Okay. And then if you expand this, basically the expectation, this is basically what we are talking about. What is F here? F is basically a convex function. Okay, so it is a convex function that we also assume f of 1 is equal to 0. So this is another condition for that. And if you use different convex functions, you get different notions of distance or divergence. For instance, the K divergence that we talked about corresponds to the case where your function f is t log t. And it's not hard to see that it's a convex function. The total variation distance, this is another distance that we talk about, is also an example of an F divergence. Okay, so this can be written as or described by this convex function. Another notion, which is also quite popular, especially in the context of training generative adversarial networks, as we're going to talk about, is the Jensen-Shannon divergence. Okay, and the idea is that this is basically a symmetrized or a smooth version of KL divergence. Okay, so it can be written in this form, and KL in particular is not necessarily symmetric, meaning that the KL divergence between P and Q is not necessarily the same as the KL divergence between Q and P. And it also has some other shortcomings, but Jensen-Shannon divergence is indeed a distance, and it is symmetric. Okay, so this is basically the first class of distances between distributions, F divergences, for some convex function f. Another class of distribution distances between distributions is basically A Wasserstein distance, or Kontorovich-Rubinstein metric, which is written in this form. So it looks basically somewhat complicated, but what it tries to say is it tries to capture the cost of moving basically samples generated from one distribution, let's say Q, to another place. Okay, so to the samples that are generated from the second distribution P. Okay, so in particular, we're going to basically find a joint distribution pi, okay, between Q and P that minimizes the distance between samples that are generated from P1 and samples that are generated from Q and samples that are generated from P. Okay, and A here is basically something that is 1 or larger. For instance, we can have one Wasserstein distance where A is equal to 1. Again, this is a very important notion of distances that is frequently used when we train generative adversarial networks, as we're going to talk about. But you can also have other and larger A values. Okay. Okay. So therefore, as we mentioned, the task of variational inference is about learning an underlying distribution with a parametric class of distributions, okay, by minimizing the distance between these two. Okay, and it turns out that we can kind of think of these tasks as some sort of a game, and this is basically the main goal of the field of generative adversarial networks. Okay, so let's talk about that. Okay. So what's the idea here? And it's a very elegant idea. The idea is that if I think of PW as a good estimator of Q, it is a good estimator if a skilled discriminator cannot distinguish samples that are coming from the true underlying distribution Q and samples that are generated by our parametric approximation PW. Okay. In particular, what we're going to assume is that we have some generator, which is described basically by this distribution PW, that takes some random noise and basically transforms that to some nice distribution that aims to approximate the underlying distribution. We call that the generator. Now we have a discriminator that its aim is to determine whether the samples that it sees are coming from the true distribution in particular whether they are real, or they come from the our approximation. So they are generated by the generator. So they are real or hallucinated samples. Okay, and we can sort of think of these two as agents with competing goals. Okay, so the generator wants to fool the discriminator, and the discriminator aims to basically recognize whether a sample is generated by the generator or not. Okay, such that if we form a kind of a game between these two, for instance, a zero-sum game, as we're going to see, then at equilibrium, hopefully, these two are reach a point where the samples generated by the generator are so good that this discriminator cannot tell whether they are real or fake. Okay, so this is the main idea behind GANs. Okay, so we have a zero-sum game between two players with competing goals. One tries to generate fake data. We call that the generator, and the other one tries to distinguish fake data from real data, and we call that the discriminator. So here's the process. So the generator, let's say, takes as input some random noise. Okay, let's say they come from a normal distribution, multidimensional normal distribution, and generator is some neural network. So in particular, it has parameters x. Okay, now from this noise, and once it is, let's say, well trained, it is going to generate some nice-looking images, for instance. So we call them fake images or hallucinated images. Okay. Now, on the other side, we have actually real images, let's say, from the training side. Now, we're going to use both of these, again, in an iterative process to train both the generator as well as the second agent, the discriminator, which is, again, a neural network with parameter y. Now, the goal of the discriminator, as I mentioned, is to basically look at these samples and decide which one is real and belongs to basically the training data, and which one is hallucinated and is generated by the generator. Okay, so this is again the main idea and the main procedure to train generative adversarial networks for the sake of generative modeling. Okay, and again it is intuitive to call these adversarial networks because again they have these competing effect or competing goal. Okay. All right, so let's talk a little bit more mathematically about what the actual zero-sum game is, and basically what is the best strategy for the discriminator and the generator. Okay. All right. So the main objective that was proposed in the original generative adversarial network paper is to solve this min-max optimization task given in equation 5. Okay. So we have some utility function. Okay, so one agent, the generator, wants to minimize that. The other agent, the discriminator, wants to maximize that. Okay, so therefore it's a zero-sum game. Okay, payoff of one is the minus of the payoff of the other one, so the sum is equal to 0. Okay, all right. So what's this payoff function? It is written in this specific form. Okay, so the main idea here is that we think of our discriminator as a binary classifier. Okay, so its goal is to look at the input image and tell whether it is that image is real or fake. So whether it belongs to class, let's say, 0 or class 1. So the discriminator is a binary classifier, and we can kind of think of this log of d, right? So this is the log of the output of the discriminator as the score of a specific sample z. When this score is high, then we can interpret that as follows: discriminator thinks this particular image with this high score is a real image. Okay. On the other hand, we can think of this as the score associated with the sample being a fake image, a hallucinated image. Okay. So what is this? So basically, Gx capital Z is the output of the generator. The generator takes this noise capital Z and generates an image. Now we feed that to the discriminator, okay? And log of 1 minus of the output of the discriminator is basically the score that we are associating to this image to say whether that is whether it's a fake image. Okay, so in particular, if this is let's say this is equal to, let's say, very small. So if log of this is let's say near 0, then the score corresponding to the fake data is actually really low. Okay, so it basically means that the discriminator is thinking that this is actually a real image. Okay. Okay. So that's why we are optimizing this objective. Okay, so we want to basically the discriminator wants to maximize the score associated with real images and minimize the score associated with the fake data. On the other hand, the generator wants to increase the score of the fake data by maximizing this quantity. Okay. So what's the best strategy for these two agents? In particular, what is going to happen in the equilibrium? Okay. If we do some simple calculation, we can find that the best strategy for the discriminator is going to be given by equation 6. The best discriminator, if you will. Okay. So what does this equation say? So this basically is saying that if let's say that I'm talking about I want to decide whether a specific image, let's say Z, is real or not. If this value is near 1, then discriminator thinks that this image is real. If this value is near 0, then the discriminator thinks that this is a fake image. On the other hand, if this value is exactly equal to half, then it means that the discriminator cannot decide whether this image is real or fake. So this is essentially the best case scenario from the perspective of the generator. Okay. Now, if I have a really bad generator, okay, then it's not gonna give a really good score to a real image. Okay. So because the distribution that it determines is not going to be a good representative of the underlying true distribution. So what does that mean? It means that for real images and bad generator, this value is going to be really small, such that the ratio is equal to 1. Okay, so that's the case, therefore, where the discriminator can very well say whether the image was real. In particular, when we don't have a really good generator. Okay. And similarly, if I feed a fake image here, okay, the Q for the fake image, let's say, is low. Okay, then what will happen is that the discriminator again can tell that this is not the best. This is not a real image, as long as PG is not equal to the true underlying distribution. Okay, so therefore this is the best strategy for the discriminator. Which we can find quite simply by just again finding what is the maximum D, what is the D that maximizes the utility for any given generator. All right. Now what we can do, we can plug this into our problem equation 5 and find basically the optimal strategy for the generator. What's the best generator? Okay. And if we do that, we're going to see that the optimal strategy for the generator is actually going to be given with this equation 7. So up to some constant, the optimal strategy is the one that minimizes the Jensen-Shannon divergence. One example of F divergence that we talked about before between the distribution described by the generator as well as the underlying distribution. Now, if I have a very powerful neural network, I can assume that this distance will be 0. So what does that mean? It means that in the best case scenario, the generator can perfectly learn the true distribution Q. Okay. So what is happening? At equilibrium, where both of these are at their best strategy, meaning that basically the best discriminator is given by equation 6, and the best generator is the one that basically makes sure the Jensen channel divergence here is equal to 0, what will happen is that it's going to perfectly learn Q. So if I plug that into equation 6, we'll see that for any sample, whether it is real or not, the discriminator won't be able to tell whether the sample is actually coming from the generator or not. Okay, so it means that therefore at equilibrium we're going to achieve what we are looking for. We have a really strong model that can perfectly learn and sample from the true underlying distribution. Okay. All right. So there is a natural question here, and actually there are two natural questions. First of all, here we see the Jensen channel divergence, and one question is why this Jensen channel divergence, and whether we can replace it with other F divergences. And if we do that, what is basically our training problem? Okay. And the second question is, well, what's the connection with variational inference that we talk about? So we said that we want to minimize the Jensen channel divergence and or other divergences, and that turns out to be a game. Okay. So here in this slide, we basically showed how we can go from the game setup, the min-max setup, to minimizing the divergence. But can we also go from the divergence to a min-max problem, to a gain problem? So these are questions that we're going to answer in the next part of this lecture. I'll see you there.